If you are preparing for that next big career move, specifically tackling low-level design or LLD, interviews in software engineering, you know the territory. It's not just about coding. It's about, architectural wisdom. And that wisdom is really codified in design patterns. These are the 23 standard solutions to common problems that, well, they act as a shared language across the whole industry.
That's absolutely right. And too often, developers treat design patterns like a static list to be memorized. They'll study the definitions, the UML diagrams, but the best interview answers. They show that you understand the why. Why does this pattern exist? What trade-off is it managing? Interviewers, they want to see you reach for a proven playbook, not, reinvent the wheel in some brittle way.
So our goal today is to give you a shortcut to that architectural wisdom. We're going to cover all three major pattern groups, creational, structural, and behavioral, and give you the sharpest analogies and the technical nuggets you need to confidently articulate why and how you use them. We're really aiming to give you the foundation to sound genuinely expert.
And we won't stop there, because real-world systems aren't single-threaded, are they? So we're dedicating a good chunk of time to the most critical related topic in LLD and system design: distributed concurrency control. That is where the rubber really meets the road when you're building robust, scalable applications.
Okay, let's unpack this. Starting with the fundamentals. Creational design patterns, the ones that dictate how objects come into existence.
Right, so creational patterns exist because, object creation often involves a level of complexity that should really be hidden from the client. They abstract the instantiation logic. They decouple the consumer of the object from the details of its construction. And this is just crucial for systems that need flexibility around what classes they instantiate.
Let's begin with the prototype pattern, which we're calling the clone. The goal seems pretty clear: efficient copying.
Correct. The prototype pattern is all about creating a copy or a clone of an existing object, especially when constructing that original object is computationally expensive. Imagine a heavy robot-based object that takes, say, seconds to initialize. You don't want to run that whole routine every single time you need a slightly different version.
You just want to stamp out copies.
Exactly.
But just, standard copying mechanisms like manually setting fields or using simple copy constructors, they run into some serious issues, don't they? What are the two key problems the prototype actually solves?
That's the core interview question right there, the cloning dilemma. First, you have what you could call an encapsulation breakdown. If a student object has private instance variables, the external client that's trying to make the copy, well, it just can't access them. It's blocked by the access modifiers.
Okay, so you can't get to the private stuff. And the second problem relates to what? External knowledge?
Precisely. It's the client knowledge burden. So, if that student object has 100 fields, but maybe 98 need copying, and 2, like an auto-generated ID or a temporary session token, should not be copied.
Yeah.
The client shouldn't need to know that specific business logic.
Right.
And if that logic changes, maybe now only 95 fields need copying, you've just broken thousands of client classes that were depending on that old knowledge.
So the prototype pattern solves this by basically keeping the logic where it belongs.
It delegates the responsibility for cloning to the object itself. The original object implements a prototype interface, and it exposes a generic clone method. When the client calls clone, the object runs its own internal cloning logic.
Yeah.
And because the object is cloning itself, it has full access to all its private members, and it has the complete up-to-date logic for what fields to copy.
So it preserves encapsulation and guarantees everything is consistent.
Exactly.
This brings up a quick technical point, and it's definitely relevant for an interview. When you're cloning, you have to decide between a shallow copy and a deep copy.
Oh, that's a highly valued detail to bring up. A shallow copy will replicate the main object, but it only copies references to any complex or mutable subobjects it contains. So if you modify a subobject in the clone, you're also modifying it in the original object, which is usually a big problem.
That sounds like a bug waiting to happen.
It is. A deep copy, which is typically what you want with the prototype pattern, recursively clones every single mutable subobject. This makes the original and the clone completely independent. It ensures the integrity of the whole object structure.
Okay, so moving from copying to restricting, let's talk about the singleton pattern, the one and only. It's often the first pattern people learn and maybe the most debated.
The goal is just strict control. Restrict instantiation of a class to one and only one object. We use this for things like a thread pool, a configuration manager, or maybe a hardware interface driver where having multiple instances would just lead to chaos or waste resources. The mechanism is simple. Private constructor, public static get instance, method.
The real depth here, though, it seems to lie in achieving thread safety without a huge performance penalty. We have those 4 key methods. Let's start with eager initialization.
Eager initialization is the simplest way. The object gets instantiated right when the class is loaded by the class loader using a static block. It's inherently thread safe because the object exists before any concurrent threads can even try to access it.
But the downside is...
Well, it violates lazy loading. The resource is consumed even if your application never actually uses that singleton instance.
And if we try to make it lazy, we run straight into concurrency problems, which leads people to use synchronization.
Yes. The naive lazy initialization, it just checks for null in get instance and creates the object if it's null. But in a multi-threaded environment, 2 threads can check at the same time, both find it's null, and both go on to create an object, which completely violates the singleton constraint. So the quick fix is to slap synchronize on the entire get instance method.
Okay, that solves the thread safety problem, but it introduces a massive performance bottleneck, right?
Precisely. That synchronize method fix is, well, highly inefficient. After the singleton object has been created, say, on the very first call, every single subsequent thread that calls getInstance still has to wait to acquire and release the lock. Even though the logic inside is now trivial, it's just returning a reference. The overhead of that constant locking is just significant and totally unnecessary.
Which is why we rely on double-checked locking as the kind of optimized standard.
Double-checked locking, or DCL, is the industry solution to reduce that lock contention. So we check for null before the lock. This minimizes the expensive locking step. Only if the object is null does the thread enter a synchronized block. And critically, we check for null again inside the synchronized block.
Why the second check inside the lock? That's the part that always trips people up.
Right, because multiple threads might be queued up waiting for that synchronized block. If thread 1 exits after creating the object, thread 2 immediately gets in. Without that second check, thread 2 would just go ahead and create a second instance. The second check inside the lock makes sure that only one thread ever initializes the object. This is the efficient, lazy, thread-safe way to do it.
I have to pause here because, in interview prep, we should probably also mention the big industry critique. Why do so many architects consider the singleton an anti-pattern today?
Oh, this is a critical insight, especially for a senior developer level. Singletons introduce global state. That makes your components tightly coupled and extremely difficult to test. When you're unit testing a class that depends on a singleton, you can't easily swap out the singleton for a mock version. Your tests become brittle. And another thing, if the singleton implements serialization, you have to handle a special read resolve method to prevent multiple instances from being created during deserialization. It just adds complexity.
So it's a resource management tool, but it often sacrifices maintainability.
And testability, big time.
Excellent point. Okay, let's move on to the factory method pattern. This is often described as centralizing the construction process.
The factory method pattern's goal is to keep complex object creation logic contained within one dedicated factory class. The problem we're solving is scattered object creation. Client classes everywhere doing new circle, new square, new rectangle. That creates a massive amount of rigidity in your system.
Rigidity because of the maintenance burden.
Exactly. If the business logic for creating a circle changes, maybe now it needs a specific default color or some complex validation, you have to go update potentially thousands of client locations. But by contrast, using a shape factory with a single create shape string type method means all that instantiation logic is consolidated. Any change is contained right there in that one factory class.
And this directly enforces one of the most important principles in object-oriented design, the open-closed principle. That's a key interview nugget.
Absolutely. The open-closed principle, or OCP, states that software entities should be open for extension but closed for modification. The factory method follows this perfectly because if you introduce a new shape, say a triangle, you extend the system by adding a new class and just updating the factory method's logic. You don't have to modify any of the client code that uses the factory. The clients remain closed to modification.
Now, if we need to create related families of objects, we graduate to the abstract factory pattern, the so-called factory of factories.
This pattern is a higher level of abstraction. It provides an interface for creating entire families of related, dependent objects without the client ever needing to know the concrete classes involved. The analogy works really well here. Instead of one giant factory making every car part, you have specialized factory families. You might have an economic car factory that returns economic tires, economic dashboards, and economic engines, and then a luxury car factory that only returns luxury components.
So how does the client actually start this process? It seems like it requires multiple creation points.
Well, the core structural difference here is the presence of a factory producer. The client doesn't call the specific economic or luxury factory directly. It asks the factory producer for the type of factory it needs, like, give me the luxury factory. Once the client gets that specific factory object, it then uses that object to request the specific products within that family, something like luxuryfactory.create tire.
So it's a two-step process.
Right. And it allows you to swap out entire sets of dependent objects just by changing which concrete factory the producer gives back.
And finally, for this section, the builder pattern, which is all about solving the problem of overly complex constructors.
The builder pattern targets objects that need step-by-step construction, often because they have dozens of parameters, or maybe the construction steps have to be done in a specific validated order. The anti-pattern it replaces is something called the telescoping constructor, where you create multiple constructors with more and more optional parameters.
Oh yeah, I've seen that. It leads to massive constructor sprawl, and it's super confusing.
It's a mess.
So the builder pattern replaces that confusion with that clean method chaining. What are the four components we have to detail here?
Okay, so we have the product, which is the complex object being built like a custom student profile or a home. Then you have the builder, which is an abstract interface defining all the potential steps, like set address, set roof, and crucially, the setter methods in the builder return the builder object itself. That's what enables that fluid method chaining syntax developers love. The builder itself just acts as a mediator, holding the parameters for a bit.
And where does the director fit into all this?
The director's job is orchestration. It defines the specific mandatory sequence of steps you need to build a common configuration of the product. For example, to build a Cape Cod house, you must do step A, then step B, then step D. A different director could use the same builder steps to construct a colonial house. It completely separates the construction steps from the construction sequence.
And the final, critical step.
The builder implements the ultimate build method. This is the single final call where the builder takes all the accumulated validated parameters it's been holding and uses them to construct and return the fully initialized product object.
So the client only ever gets a fully complete, valid object.
That's the guarantee.
All right, now that we know how to instantiate objects intelligently, let's explore structural patterns. These govern how we combine classes and objects into larger, more flexible structures, and they often favor composition as a relationship over rigid inheritance, the ISA. And the perfect starting example is the decorator pattern.
The decorator pattern is all about dynamically adding new functionality or responsibilities to an existing object without permanently changing its class structure. We call this runtime extension. The standard analogy, the pizza, holds up perfectly. You start with a simple base pizza and you dynamically wrap it with extra cheese or mushroom layers.
And the fundamental problem it's solving is that class explosion we mentioned earlier, which happens when you try to use inheritance to handle all the combinations of features.
Precisely. If you use inheritance, you would need a new subclass for every single combination of toppings. 10 toppings leads to, hundreds or thousands of classes. It's unmanageable. The decorator pattern uses composition of layer objects. The decorator class, say mushroom decorator, implements the same interface as the base pizza.
So it is a pizza component.
Right. And it holds a reference to the base pizza it's wrapping.
So it has a pizza component.
Exactly. Both.
And that layering technique is what gives you the true flexibility, avoiding those endless subclasses.
It does. It also adheres beautifully to the single responsibility principle, or SRP. The core base pizza only handles the base cost and description. The mushroom decorator only handles the logic and cost for mushrooms. By adding complexity in these small composable wrappers, you avoid these huge complex classes that try to do too many things. It just leads to cleaner code.
Next, the proxy pattern, which is fundamentally a stand-in way to control access.
The proxy pattern acts as a surrogate, or a placeholder for another object. It provides controlled access to that original, real object. The client interacts with the proxy, and that proxy implements the same interface as the real subject it's representing.
What's the advantage of putting that proxy in the middle?
Well, the proxy can perform actions either before or after it delegates the request to the real object. This is often used for security validation. For example, a protection proxy can check if the user calling the delete user method is in fact an admin before it ever forwards the call to the actual user DAO object.
And you mentioned there are specific types of proxies that are crucial to know for a deep dive interview.
Absolutely. The protection proxy handles security, like we said. But you also have the virtual proxy, which handles lazy initialization. It waits until the client first requests the expensive real object before it actually creates it. This saves startup time. And then there's the remote proxy, which acts as a local representative for an object that's located in a different address space, maybe on another server. It manages all the complexity of network communication, kind of like an RMI stub.
Being able to articulate the difference between those three really shows a high level of technical understanding.
It does.
Okay, moving on to the composite pattern, which brings order to hierarchy.
The composite pattern is tailored for situations where you have objects that naturally organize into a tree structure, so objects that contain other objects. The goal is simple. Let the client treat individual objects, the leaf nodes and collections of objects, the composite nodes, in a uniform way.
The file system analogy just illustrates this perfectly.
Yes, a file is a leaf. It can't contain other file system components. A directory is a composite. It can contain files and other directories. The key structural requirement is that both the file and the directory implement a common component interface, say file system component, with operations like print size or ls.
And when you call an operation on the composite, it uses recursion to go down the tree.
Correct. When the client calls ls on the top-level directory, that directory iterates through its internal list of children. If a child is a file, it just performs the leaf operation. If the child is another directory, another composite, it recursively calls ls on that child. This ensures the operation propagates down the entire tree structure until every node has been processed.
Next, the adapter pattern, the translator.
The adapter pattern is a classic. It acts as a structural bridge between two incompatible interfaces, allowing them to collaborate. You have a client, the one making the request, and the adaptee, the object with the useful functionality, but the wrong interface.
Give us the implementation details again using that weight machine example.
Okay, so we have the weight machine, which is our adaptee, and it only returns weight in pounds. The client requires kilograms. So we build the adapter class, the weight machine adapter. This adapter implements the target interface, so it has a get weighting method. Internally, the adapter holds a reference to the incompatible adaptee. When the client calls get weighting K, the adapter calls the adaptee's method to get pounds, performs the conversion, pounds 2.2, and then returns the result in the client's expected format.
It's all about conversion and compatibility.
That's it.
Now, a pattern that's often confused with the adapter is the bridge pattern. Why is that? They both seem to decouple things, but in fundamentally different ways.
This distinction is crucial for interviews. The adapter solves a problem that exists after two things are built. They're already incompatible. The bridge pattern solves a problem that exists before they are built. It prevents tight coupling from forming in the first place, allowing an abstraction and its implementation to vary independently.
How does it prevent that coupling in the living things example?
Well, if we tightly couple the living thing, the abstraction, with its breathe process, the implementation, inside the same inheritance hierarchy, then adding a new breathing method, say subterranean respiration, forces you to modify or create a new subclass for every single existing living thing type.
So you're changing dogs, fish, trees.
Yeah.
You're making modifications in way too many places.
Exactly. The bridge pattern solves this by separating the two concepts into two distinct class hierarchies. The specific action logic, the implementation, like land breathe, water breathe, it lives in its own hierarchy, implementing a common breathe implementer interface. The abstraction, the living thing class, holds a reference to this implementation interface and just delegates the action to it. So now you can add a new living thing type without changing the breathing classes, and vice versa. Both dimensions can scale independently.
Hence the name bridge. It connects two flexible, independent shores.
Exactly.
Next up, the facade pattern, which is the system simplifier.
The facade pattern is fundamentally about simplifying the client's view of a complicated system. It provides a single unified interface that hides the complexity of a massive subsystem.
We discussed two main use cases. Let's expand on that second one, hiding complex orchestration.
Okay, think about initializing a complex piece of hardware, maybe a smart home system or an air conditioner. To truly turn the AC on, the process might involve 10 sequential steps. Check voltage, engage the external compressor, initiate the internal fan, set the default temperature, log the startup event.
A whole bunch of things.
Right, and these calls might span 5 or 6 different internal classes. The AC facade exposes just one simple method, turn on AC. Internally, it manages that whole 10-step orchestration sequence, insulating the client from it. So if the AC manufacturer changes the startup sequence to 12 steps next year, only the facade needs updating. The client code is never touched.
That adherence to the open-close principle again. Finally, the flyweight pattern, the memory saver.
This pattern is purely a performance and memory optimization tool. It's essential when you have to create an extremely large number of fine-grained objects, and the memory consumption of those objects becomes prohibitive. The robot army analogy is perfect for this. They're creating millions of objects, where the only thing that's different is their position, but every single object is holding a heavy shared graphic asset, the sprite.
And the key is distinguishing between two types of data.
Yes. We differentiate intrinsic data, which is the flyweight, and extrinsic data. Intrinsic data is shared among all the objects. It's the data that stays constant regardless of the instance. So the heavy sprite object itself or the robot's fundamental type. This is the only data that's actually stored inside the flyweight class.
And the extrinsic data.
Extrinsic data is what changes based on client input, like the robot's dynamics axis and the axis position. This unique data is not stored in the flyweight object. Instead, it's passed as a parameter to the flyweight object's methods. Something like display acts as the axis.
And that's what massively reduces the memory footprint per object. And what's the mechanism that ensures that heavy intrinsic data is truly shared?
We use a flyweight factory, which acts as a cache, usually a hash map. The factory is keyed by the intrinsic data, for example, the robot type. Before creating a new humanoid robot object, the factory checks its cache. If the humanoid robot already exists in the cache, it returns that single shared instance. If it doesn't exist, then it creates the expensive object, puts it in the cache, and returns it.
So this guarantees that whether the client requests one humanoid or 500,000, only one copy of that heavy 31K to B sprite object is ever loaded into memory.
That's the optimization.
Okay, we've created our objects and we've structured them cleanly. Now we tackle behavioral patterns. These govern the intricate dance of communication and responsibility distribution, making our software flexible and maintainable during execution. Let's start with the state pattern.
The state pattern is brilliant because it allows an object to alter its behavior when its internal state changes. To the outside world, the object appears to have completely changed its class, even though it hasn't. It just delegates its behavior to a separate object that represents its current state.
The vending machine is the perfect illustration of this delegation, isn't it?
It is. Imagine the vending machine object itself. It has methods like insert coin and select product. When the machine is in idle state, calling insert coin changes the machine's internal state to working state. But if the machine is already in working state, calling insert coin might just add to the current balance. The machine delegates the execution of those methods to whichever concrete state object it's holding a reference to.
And that separation of concerns is why this pattern is so valuable.
Exactly. The logic for what happens in the idle state is entirely contained within the idle state class. The logic for transitioning to the next state is also right there. This avoids having these massive, brittle if-else-if blocks inside the main vending machine class that are just checking if current state equals ideal then.
Yeah.
If you need to add a new out-of-order state, you just create one new class. You don't have to touch the existing idle state or working state at all.
Next, the observer pattern, the classic one-to-many communication model.
The observer pattern defines a dependency, so that when one object, the observable or subject, changes state, all its dependents, the observers, get notified automatically. You can think of a stock market feed. The stock price is the observable, and all the investor dashboards watching that stock are the observers.
How is this mechanism maintained internally?
The observable holds an internal collection, a list or a set of references to all the observers that have registered themselves via an addObserver method. When the observable state changes, for example, a new price is set via setData, it just iterates over this list and calls a generic update method on every single registered observer. It's a decoupled broadcast mechanism.
Let's discuss the two common notification strategies here. Push versus pull. That's a good interview point.
It is. In a push model, the observable, when it notifies, pushes all the relevant state data to the observer, usually through the update method signature. This can be pretty inefficient if the observer only needed one small piece of that information.
Right.
In a pull model, the observer gets only a minimal notification, maybe just a pointer back to the observable, and then it's the observer's job to call back to the observable to pull only the data it needs.
So the pull model is generally more efficient and flexible.
It is, because observers only retrieve what they actually require.
The strategy pattern is all about swapping out behavior at runtime.
Strategy defines a family of algorithms, encapsulates each one behind a common interface, and makes them interchangeable. This is really common when a piece of logic, the overall task, can be achieved in several different ways. The classic example is payment processing. The task is pay, and the strategies are credit card strategy, cash strategy, or UPI strategy.
Before we move on, let's just quickly define UPI for our global audience.
Good point. UPI stands for Unified Payments Interface. It's a common real-time payment system used very widely, especially in India. But regardless of the regional payment system, the concept is the same. The client needs a way to pay, and the specific algorithm for validation, authorization, and funds transfer. That's the strategy.
And how does the client maintain its flexibility?
The client, say the shopping cart, holds a reference only to the common interface, pay strategy. It is completely unaware of whether it's holding a credit card object or a UPI object. At runtime, the client dynamically receives the desired strategy object, new credit card strategy, for example, and then it's just called the generic pay method.
Which means you can add a new payment method, like a Bitcoin strategy, without ever modifying the shopping cart class.
There it is again, OCP in action.
Next, the chain of responsibility pattern.
This pattern lets a request be passed along a sequential chain of potential handlers. The sender doesn't know, and frankly doesn't care, which object will ultimately process the request. The request just enters the chain, and the system tries one handler after the next.
The logger system is the easiest way to visualize this flow, I think.
For sure. In a logging chain, the client sends a message, maybe marked as debug level. The request hits the info-log processor first. Can it handle debug? No. So it passes the request to its successor, the debug processor. Can this processor handle debug messages? Yes. It logs the message, and in this case, it might stop the chain, or it could continue passing it on, just depending on the design.
And what defines the actual structure of the chain?
Every processor class implements a common interface, and crucially, holds a reference to the next processor in the sequence. If the current processor can't handle the request, it simply delegates the responsibility by calling nextprocessor.handleRequest. This structure lets you modify the order of the chain or add and remove processors without ever impacting the client that's initiating the request.
The template method pattern. This is about standardizing the framework of an algorithm.
This is a classic behavioral pattern that really focuses on inheritance. It defines the mandatory skeleton or sequence of an algorithm in a base class, but then it allows the concrete subclasses to redefine or implement certain specific steps.
What's the key technical constraint that's used to enforce that skeleton?
The parent, the abstract class, defines the main template method. Let's call it process transaction. And this method absolutely must be declared as final. Making it final prevents any subclasses from overriding the overall sequence.
Got it. So the flow is locked in.
Right. The template method dictates the flow. Step 1, validate. Step 2, debit. Step 3, calculate fee. Step 4, credit. The specific implementation of those individual steps, like calculate fee or validate, is defined using abstract methods, which the concrete child classes, like pay-to-friend transaction, must implement. They provide their own unique business logic for that specific step.
Moving on to the command pattern, which converts a request into an actual object.
The command pattern decouples the object that invokes an operation, the sender, from the object that knows how to perform it, the receiver. This is vital when the initiation of the action is separated in time or space from its execution, or maybe when the execution logic is really complex.
I want to challenge this a bit. Why not just have the sender call the receiver directly?
That brings us right back to tight coupling. If the sender calls the receiver, the AC object, directly, it needs to know the complex internal API of that receiver, all 10 sequential steps required to turn it on. If you wrap those 10 steps into a single turn-on command object, the sender only needs to know about one generic execute method. The command object holds all the complexity and a reference to the receiver.
And the benefits of making the request an object are massive.
They really are. Once the request is an object, you can queue it for later execution, you can log it, and most importantly, you can implement undo-redo functionality. If the command object holds the state necessary to reverse its operation, maybe by storing a memento of the state before execution, reversing the operation is as simple as calling unexecute on the command object itself.
And that naturally leads us to the memento pattern, the engine behind the undo function.
The memento pattern is specifically designed to capture and externalize an object's internal state so that it could be restored later, all without violating encapsulation. It relies on 3 actors.
Can you detail the 3 components and their roles for us?
Sure. First, you have the originator. That's the object whose state we need to save. A text editor, for example, or a configuration originator. It has methods to create memento and restore memento.
Second, the memento.
The memento is the snapshot object. It holds the internal state fields that need to be preserved. This is where the encapsulation challenge gets solved. The memento is often created by the originator, and sometimes it uses language-specific features, like inner classes, to allow only the originator to access its internal state, while keeping it opaque to the third component.
And the third component, the caretaker.
The caretaker is the history manager. It manages the list of stored mementos, which represents the history or the undo stack. It handles add memento and the undo operation, which retrieves the last memento object and passes it back to the originator for restoration. And crucially, the caretaker can store and manage mementos, but it cannot access or modify the state inside them. That's how it preserves the originator's encapsulation.
We have several other important behavioral patterns that we should probably quickly explore just to ensure we cover the full technical range expected in, advanced LLD discussions. Let's look at the iterator pattern.
The iterator pattern provides a standard way to access the elements of an aggregate object, a collection sequentially, without exposing the underlying implementation details. So whether you are looping through a standard Java array list, which is backed by an array, or a linked list, which is backed by nodes, the iterator interface has next. Next stays the same.
Which simplifies the client code.
Right. And it allows the collection's internal structure to change independently.
What about the visitor pattern?
The visitor pattern is useful when you have a stable class structure. The element classes like room, carriage, and part, and you frequently need to add new operations across all those classes. So instead of modifying every single element class every time you introduce a new operation, which would violate OCP, you define the new operation in a separate visitor class, maybe an export visitor or a tax calculation visitor. The element classes simply accept the visitor, and the visitor does the work. It lets you add features without altering your existing code.
Then there's the mediator pattern, designed for complexity management and communication.
Mediator is crucial for loose coupling. When you have a lot of objects, colleagues that need to interact, but direct communication between them becomes a chaotic mess of tight dependencies.
A spaghetti of connections.
Exactly, an n-squared problem. The mediator steps in. The colleagues communicate only through a central mediator object, like an auction room or a chat room. The mediator handles all the routing, ensuring that if one colleague changes, you only have to update the mediator, not every other colleague it talks to.
And finally, the interpreter pattern.
The interpreter pattern defines a formal grammar and a way to evaluate expressions written in that grammar. So if you need to build simple languages or rule engines, or parsers, like a simple arithmetic evaluator for A plus BC, you would define classes for terminal expressions, the operands like A, B, and C, and non-terminal expressions, the operators like plus and multiply. It's less common in everyday applications, but it's essential if you're building domain-specific languages or configuration parsers.
Okay, we've covered the entire playbook of design patterns. Now let's shift gears entirely and move into the technical core of system design and LLD. Distributed concurrency control. This is where the concepts really get tested under load in a multi-machine environment.
Here's where it gets really interesting. Because while patterns make your code clean, concurrency control is what makes the system functional and reliable. We absolutely must prevent massive data consistency failures when multiple users are trying to access the same resource.
Let's revisit that critical failure scenario, the triple booking in the movie theater. If 3 requests read the same seat simultaneously as free, and all 3 of them succeed in updating it to booked, we have a revenue disaster and some very angry customers.
That data inconsistency is the heart of the problem. And as you correctly pointed out, in a modern distributed microservice architecture, simply using local synchronized blocks is worthless. If those 3 booking requests land on 3 different server instances, machine A, B, and C via a load balancer, they're running in separate Java virtual machines.
So their local locks are totally irrelevant to each other.
Completely.
So we have to rely on the shared resource, the database, to manage the distributed concurrency. And this requires fluency in some foundational concepts, starting with the absolute core, transactions.
Transactions are the essential unit of work. They ensure database integrity. We rely on the ACID properties, especially atomicity. Atomicity ensures that a sequence of operations is treated as a single, indivisible unit. All operations must succeed, which is a commit, or if any part fails, all of the successful operations must be undone, which is a rollback. Without this, you get horrible inconsistencies, like a debit succeeding, but the corresponding credit failing permanently.
And how do transactions enforce this when other people are trying to read or write? That's DB locking.
Locking is the mechanism for mutual exclusion. We primarily use 2 types. The shared lock, or S-lock, also called a read lock, is taken when a transaction just wants to read data, Multiple transactions can hold an S-lock on the same row at the same time. The key restriction, though, is that an S-lock prevents any other transaction from acquiring an exclusive lock, an X-lock, or a write lock.
And the exclusive lock.
The exclusive lock, or X-lock, is taken when a transaction intends to modify the data. Only one transaction can hold an X-lock on a given array at a time, and an X-lock is highly restrictive. It prevents all other transactions from taking either an S-lock for reading or another X-lock for writing until that lock is released.
So it's the ultimate barrier against concurrent modification.
It is.
This leads us into the heart of the complexity. Isolation levels. This is the explicit trade-off between consistency and concurrency. The higher the isolation, the more consistent the data, but the fewer parallel operations the system can handle.
And to master the isolation levels, you absolutely have to master the three phenomena, the three problems they are designed to solve.
Okay, problem one, the dirty read.
This is the most dangerous one. A dirty read happens when transaction A reads data that transaction B has written but is not yet committed. So if transaction B subsequently fails and rolls back, the data that transaction A read is now garbage. It was based on an invalid, non-persistent state.
Problem two, the non-repeatable read.
This is less about garbage data and more about consistency within a single transaction. So transaction A reads a row, and before transaction A is finished, another transaction, transaction B, commits a modification to that specific row. Now, if transaction A reads the same row again later in its process, it gets a different value. To transaction A, the data seems to have just changed magically during its runtime.
And problem three, the phantom read.
This is similar to the non-repeatable read, but it applies to a whole set of rows that are defined by a range query. So transaction A runs a query, like select where amount 100. Then a committed transaction B inserts a new row where the amount is 150. When transaction A runs the exact same query again, it now finds an extra row. A phantom row has just appeared out of nowhere.
And these three problems allow us to define the four standard isolation levels. Let's go through them briefly, focusing on their locking mechanism.
Okay, read uncommitted. This is the lowest level. It uses almost no locks for reading. It allows dirty reads, non-repeatable reads, and phantom reads. It gives you maximum concurrency, but basically zero consistency guarantees. You almost never use this in production. Maybe for some high-volume, low-importance logging data, but that's it.
Read committed. This is the default in many modern databases, like PostgreSQL and SQL Server.
Read committed solves the dirty read problem. For writes, it acquires an X-lock, and it holds it until the transaction commits. This prevents anyone from reading uncommitted data. However, for reads, it releases the S-lock immediately after reading the row.
So that brief locking means other transactions can commit updates right after you read.
Which leads to non-repeatable reads and phantom reads. It's a good balance, though, for general web applications.
Repeatable read. This is MySQL's default.
Repeatable read solves the dirty read and the non-repeatable read problem. It achieves this by making sure that all S-locks acquired during the transaction are held until the entire transaction commits. If T1 reads a row, it holds that S-lock, which prevents T2 from getting an X-lock to modify that row. This guarantees consistent results for repeated reads of the same row.
But it still has a weakness.
It does. It typically doesn't prevent new rows from being inserted into a range, so phantom reads are still possible depending on the specific database implementation.
And finally, serializable, the strongest guarantee.
Serializable guarantees true isolation. It prevents all three problems. It uses the same aggressive S-lock and X-lock strategy as repeatable read, but crucially, it adds range locks, or predicate locks. This locks the conditions of a query, preventing other transactions from inserting or deleting rows that would match the query criteria. This level is slow, and it severely limits concurrency, but it guarantees maximum data integrity.
This detailed locking discussion leads us to the ultimate choice in concurrency strategy: optimistic versus pessimistic control. This is a critical discussion point for any system architect.
And this choice is driven entirely by the assumed conflict frequency. Are you building a system where conflicts are likely? Go pessimistic. Are they rare? Go optimistic.
Let's focus on pessimistic control first.
Pessimistic control operates on the assumption that conflicts will happen. It mandates high isolation levels, repeatable read, or serializable. It relies on aggressive, long-term locking. Locks are acquired early, often when the data is first read for an update, and they're held until the transaction finishes. It's a very conservative, high-integrity approach.
The cost, however, is significant.
The primary drawbacks are a massive reduction in concurrency and system throughput and the constant threat of deadlock. A deadlock occurs when transaction 1 holds lock A and needs lock B, but transaction 2 holds lock B and needs lock A.
And we're both just stuck.
they're perpetually blocked, and the system has to intervene to abort and roll back one of them. For high-volume systems, this cost is just unacceptable.
Now, optimistic control takes the complete opposite risk profile.
Optimistic control assumes conflicts are rare. It prioritizes high concurrency and often uses lower isolation levels like read committed. And crucially, it avoids long-term locking entirely. Transactions read the data without placing restrictive locks. Instead, they rely on versioning.
Can you explain that versioning mechanism?
Sure. When a transaction reads a row, it records the row's version number or maybe a timestamp. It does its work in isolation. When it finally attempts to commit the update, it performs a quick validation step. It checks the database to see if the row's current version number matches the version number it originally read. If the versions differ, it means another committed transaction modified the row while this one was working. The validation fails.
And the consequence of that failure?
Immediate rollback. The transaction has to be aborted and often automatically retried. While rollbacks are costly, the system avoided that slow locking overhead for the vast majority of transactions that didn't conflict. This is the basis of sophisticated modern database techniques like multi-version concurrency control, or MVCC, which is used widely in systems like Oracle and PostgreSQL. It allows readers to never block writers, which further boosts optimistic concurrency.
So the ultimate trade-off comes down to whether the cost of rollbacks from the optimistic approach is lower than the cost of constant locking and deadlocks from the pessimistic approach.
Exactly. For high-throughput e-commerce where conflicts are rare, optimistic wins every time. For an intensive accounting batch job where a rollback after hours of processing would be catastrophic, those pessimistic guarantees might be worth the reduced concurrency.
So what does this all mean? We've covered the entire range of solutions, from creational patterns that ensure controlled object initialization, structural patterns that maximize composition and flexibility, and behavioral patterns that govern efficient communication. And we finished with, really, the most critical test of system architecture, distributed concurrency control.
Fluency in these topics, not just the definitions, but the trade-offs, the consequences of tight coupling, and the underlying locking mechanisms, is what distinguishes a code writer from a system architect. You're demonstrating that you understand the standardized, proven playbook for building maintainable, flexible, and robust software.
And as we close this deep dive, let's return to that core concept of LLD risk management and leave you with the provocative thought we discussed regarding the choice of concurrency control.
Consider this again. If a high-value niche financial application were designed specifically for long-running, low-volume financial batch processing, where a single transaction might take hours to aggregate data and apply updates, which control mechanism would the architects prioritize? Optimistic or pessimistic?
The choice would almost certainly lean toward the strong, aggressive guarantees of pessimistic control, likely enforcing serializable isolation. Why? Because the cost of failure is just astronomical. If an optimistic transaction were to fail its validation check 5 hours into a process, the rollback would be too slow, too resource-intensive, and way too disruptive. The risk of the occasional deadlock or the certainty of slower throughput is the necessary trade-off to ensure the maximum possible integrity for those critical, long-running data operations.
And understanding that risk calculus is what elevates your design conversation. Keep exploring these architectural choices and let these patterns guide your next project.